put here the pen. Yeah, just in the same way in which we had that classically, a lattice gave me well, the ability to produce a torus, real or complex, a quantum lattice. If you ignore these rays right now from the fan, you just think of this Zn inside Rn, this H map into Rd. Typically, N is bigger than D, typically. Well, if it is equal to D, and this is just the canonical lattice, well, we get just the typical lattice in Rd as in classical toric geometry. But this quantum lattice was what you need to produce a quantum torus. In fact, you think of this Rd as winding about the transversal, and this foliation, well, produces this dust here in the transversal, here, and the universal cover of this transversal with this dust is this Rd with this dust. So typically the torus where the foliation is happening is of one larger dimension than D. This is just the transversal. But anyway, I have an H from Z to the D, to the N, to Rd. The image of H is the quantum lattice. But now I can move, and to have a quantum lattice is essentially the same as to have a quantum torus, because then I take Z to the D, modulo gamma, whatever this symbol is meant to mean, and then I get a quantum torus for the lattice, quantum lattice gamma. But now I have H, and I can move H, and this is a deformation parameter. Well, in Rd, here in Rd, I can put a fan. I have to make sure somehow that some of the, this is 3 dimensions, so in this picture is not very well depicted, but I have n basis vectors. And one of them goes here, and one of them goes here, and one of them goes here. In classical toric geometry, I could take the shortest primitive number theoretical generator of the rational direction, but here I can't. This direction could and often will be irrational direction, because the direction only has to land on gamma. The fan has to be a fan on gamma, and then well, I have this the images are my Planck lengths, and I could have more, of course, just not in the one skeleton of the fan, but I have to have some points in the one skeleton of the fan to set my Planck lengths on the various directions. So this is a calibrated quantum fan. Well, a calibrated quantum fund is all you need to get a calibrated from a calibrated quantum fund. You can produce a toric space given by that calibrated quantum information, where delta is the fan per se. So if you forget H and you only remember gamma, I was talking about H, gamma H. In this slide, this becomes delta gamma V. To have the images of the basic vectors of H, V's, is the same as to have H. So somehow we write it a little bit like but if I only mark the points, I have a map that forgets H and only remembers the space, and this can be identified as a sort of a bundle, sort of a circle bundle. It's actually a set gerb that has the same amount of information as a circle bundle. So to remember H or not to remember H is given by a cocycle. A cocycle with 3 indices with values in Z. And that's what this notation means in the theory of stacks, that you have this cocycle that tells you how to recover H from just having the space. This might be a little bit too particular right now. It may become more important later, but it is a nice interpretation for people that are into stacks. Anyway, I had given some examples. And this is an example that I gave in the last time. This is the example of P2. In this case, well, I'm going to just take 1, 0, 0, 1, but then I'm going to take here minus VA. And this could be irrational numbers, that's the whole point. And as I explained last time, these are the change. This is composed by 3 charts. If I took C star rather than C square, if I took C star square, this would be a quantum torus. This would be a quantum torus, and this would be a quantum torus. But these 3 quantum tori would be isomorphic. You would have 1 quantum tori given for every one of these cones. And these matrices that are deliberately labeled 1, 2, 2, 3, and 3, 1 would give the various isomorphisms between the quantum tori. So that the quantum tori Q23, that is C2 star divided by this action, this, of course, the quotient, the literal quotient is a non-house of space, but as a stack is an object. So if it has these 2 coordinates, C2 coordinates, this is the gluing map between the quantum tori here and the quantum tori here. Of course, this is a partial compactification of the quantum torus. This is a partial compactification. These are 3 different partial compactifications, and I am gluing them by these 3 gluing maps. And of course, B over A and 1 over A could be irrational numbers, but I explained last time how you could make sense of these irrational exponents to do the gluings. The basic idea is that you take the universal cover and you do the you take the logarithm and you do the gluing at the in the logarithmic cover, and then you descend. And that's what these irrational exponents mean. Anyway, here I have the gluing maps, and this gives me some quantum P2 depending on the parameters A and B. If A and B happen to be rational, then this family of quantum P2s, this P2 becomes a weighted projective space.
Could you please draw it? Draw its, I don't know, moment triangle.
Oh, yeah. It looks like this. There. Okay. But of course, this slope is irrational, typically.
So the slope is B over A or something like that?
Something like that, that's right. Yeah.
Okay.
Yeah. That's right. So now you have this non-rational polytope as the image of the moment map. In this case, this is a Kähler. This is symplectic and Kähler non-commutative space. The set of points, well, it's bad. It's not very useful because the quotient is non-Hausdorff space and non-Hausdorff space and non-Hausdorff space. It does give gluings of non-Hausdorff spaces, but it's not very useful to think of the set of points at all. It's more useful to think of it as a non-commutative space. Okay, so well, we have the following theorem. The category of simplicial calibrated quantum toric varieties and the category of quantum toric fans are equivalent. This theorem is a little bit unfair from what I have said right now, because I have not really defined by any other means the category of simplicial calibrated quantum toric varieties. And I could define it as equivariant Picard compactifications of Kähler stacks or whatever for this particular example. But I let it to your imagination that it could be defined this category of simplicial calibrated quantum toric varieties, and this term can be proved. It's in our paper. It's equivalent to the category of quantum toric fans with maps of fan. Here, the important thing is that remember that quantum fan has the kind of the combinatorial structure, the calibration. This contains the information of the quantum lattice, the image is, but also it had this funny thing where there was this mark points, J, a collection of indices of some of the images of the basic vectors of H, so a collection of points in the quantum lattice gamma that were just marked. They were just kind of there. And we carry mark points into mark points. So this category carries mark points into mark points in this category. This is important. In the quantum fan, there is these special points, and we have to carry the mark points into the mark points. This is done so that we get a nice, when we vary the parameter, the H, we get a nice modular space. We desingularize the modular space by being careful about the mark points. So we have quantum geometric invariant theory. Let me explain this in very, very explicit terms. So we have the calibrated quantum fan. Observe that right now I'm being careless again and not putting the J here, but I carry it in general in the notation. Sometimes I just write this, but I should be writing this. And so I get this, for example, think of quantum P2 that we just saw in detail. This could be quantum P2. It is the quantum Toric variety associated to the quantum fan. And so we have that information, we have that H map. And from this H map, we're going to apply the so-called Gale transform. That is very classical in convex geometry. So what we do is that we choose some A1, A2, An in Rn minus D, so that this happens. This can be written in a more invariant form, but I'm writing it like this today. So we have this, if h of x is this, and these are the VIs that are the images of the basic vectors, then I choose these vectors in Rn minus D here. So just kind of the dual picture. So we have this K, it's just this K. The Gale transform is just this K, is given by this K, is we have this sequence, well, these are the A's that give the K, and the K gives the A's. So this is so-called Gale transform of H, and then I can use this K or these A's to do the following. So I define a set of indices given to a Z1, Zn. So if I have a collection of complex numbers, I get the indices for which they are non-zero. This is very typical in toric geometry. And then I get this S set. Well, this is also very typical. It's the complement of I is a cone. So I get this set so that the complement of the I set is a cone. This is an affine toric variety, typically. And on this affine toric variety S, I make Cn minus D act to produce a foliation. If it was rational, this would not be Cn minus D. This would be a torus acting on S. But because of irrationalities in H, what I can assure is that I can produce a holomorphic foliation given by this expression. This is E as the exponential. And this action preserves S. Imagine this complicated foliation that could have leaves that are dense everywhere or anything like that, and commute with the action of the torus on this. It was an affine toric variety. It has a torus acting, and this is this foliation on this affine toric variety. So we get the quotient stack of this foliation on this affine toric variety. I use A for the action because of these A's. Remember, A's were the K's that were kind of the dual of H, the Gale dual to H. And then we have the following theorem, that the quantum P2 or the toric variety at hand given by the fan with the mark points. I told you how to produce this by charts in the previous slides, but now I told you how to produce it by something that we call quantum geometric invariant theory. Let me stop a second and ask if you follow what I just said.
Well, I'm trying to. So, yeah. So it resembles some of the classical geometric invariant theory, but
Yeah, it's very similar, extremely similar. That's why we call it this way. We had defined this by charts in the past. Well, in fact, my definition was really a colimit on a category of stacks, homotopy colimit on a category of stacks. But this is equivalent as defining it by charts. But now I'm giving you a second definition. That is I'm producing this affine toric variety. You know, just the fan structure produces an affine toric variety. This is typical in toric geometry, remember? Just the fan structure, just the combinatorics, the final toric. But in the classical,
yes.
But in the classical theory, there is a torus and there is another torus action, and the quotient is the toric variety. Here now there is a foliation on the affine toric variety, and the quotient by this foliation given by the dual of the H map is A. The Gale dual is A, gives you the foliation. The exponential of A gives you the foliation. And this exponential foliation gives you the modular space of leaves of the foliation is the same as the quantum toric variety. Is the generalization of the classical story for irrational fans. But now we have these stacks as the quotients.
Okay.
So I can do the uncalibrated version. Well, I lied to you in the last slide. I should not have said foliation. It was the group action. It was very important that it was the group action. This group action of this group for having the calibrated quantum toric variety. If I really just think of the space of leaves of the foliation, then using foliation theory, I get the uncalibrated version. But of course, the foliation has a holonomic groupoid, as in the theory of foliations, and the statification of the holonomic groupoid gives you the stack structure in the uncalibrated case. We can ignore this slide. It's just a remark that if you really want to go into the theory of foliations, then you only get the uncalibrated case, and this stopped development in this theory for a long time. It is the introduction of the calibration what allows us to move forward. Now, there is an extremely beautiful story.
Just one question. Uncalibrated is generic, right? So you need calibrated only in some special cases. So you need to like when the things are rational, or is it true or?
Yeah, this is essentially true. In the purely irrational case, you lose and gain nothing by all this rigmarole. It is, but I have to say calibrated in every case because if I don't carry out the H, if I only think of the gamma, this is the uncalibrated and this is the calibrated. I have to reconstruct all the time the calibration. But if I want to produce a modular space, it's easier to just to carry all the time H, it's there anyway, and vary this as the deformation parameter. That's why calibration is so important. The calibration is the deformation parameter of the modular space. Is the deformation chart of the modular space. So, so yes and no. It's like the calibration is very important. So So let me just mention this slide, and then I'll continue next time. But for now, let me just say that there is an incredibly beautiful theory called LBM theory. And I had mentioned this theory before. In the case of P1, what this theory gives you is the classical Hopf surface, and it's an elliptic vibration, this classical Hopf surface. So this was generalized by Calabi and Ekman for products of Pn cross Pm. They could produce some products of spheres. I don't remember what spheres. And they were no longer elliptic curves, but it was something like elliptic vibrations. Here there were some higher dimensional tori. And this was the famous, this is the Hopf surface, the very famous Hopf surface. And this is the very famous Calabi-Ekman manifolds. Combining developments by Lopez de Medrano and Berhovsky and Merseman, and even Bosio sometimes, you could take any toric variety, classical toric variety, and put a manifold here, and have something like an elliptic vibration in general over any toric variety, and obtain these manifolds. And it is more, in the classical case, it is more or less equivalent to have this manifold that is a complex manifold. But that is non-Kähler. Exactly like the Hopf surface. Hopf surface S3 crosses 1 is complex. It's a complex manifold, which is a little bit of a surprise at first, but then you realize it's clearly a complex manifold. But then, of course, just by purely topological reasons, H2 of this space is 0, of course. It has classes in dimension 1, dimension 3, but nothing in dimension 2. So it cannot have a symplectic form, because there is no, a symplectic form would produce second cohomology. So it cannot have a symplectic form, so it cannot be a Kähler manifold. So it cannot be algebraic. So it's a complex manifold that is neither Kähler, nor symplectic, nor algebraic. But that nevertheless is extremely important, very, very important. And this can be generalized rather than for P1 for any toric variety. Classical toric manifold, classical toric manifold or whatever. But the thing is that this will be also complex, non-Kähler, non-symplectic, non-algebraic manifold. And that is very interesting. It's a lot of non-algebraic complex manifolds that you have a chance at studying. And recently, very recently, Merseman, Lee, and Katsarkov and me have been studying this situation more intensely. And we have proved that these are all something called logarithmic transforms. Introduced by Kodaira, but generalized ones. Logarithmic transforms. So you take the toric variety and you do some universal operation called a generalized logarithmic transform, and you get its LBM manifold associated to it. But you see this T inside this N just for geometric intuition, can be thought of as here is n, here is the toric variety, here is n, and this can be thought of as a foliation by tori. This n can be thought of as being foliated by tori. And then one can ask what happens when I holomorphically deform this foliation. Given in the log transform of the toric variety. And what happens when you holomorphically deform this foliation is that you get at the same story, at the quantum toric varieties, the calibrated and the uncalibrated ones. So it turns out that these LBM manifolds, that is a theory that it has been developed. Just to summarize, there's a theory of manifolds called LBM manifolds that was later discovered to be intimately related to toric varieties. They are logarithmic transformations of trivial elliptic, multi-elliptic fibrations of the toric variety. And these are terms that make sense in the world of complex geometry. That is non-algebraic complex geometry. But it is unsurprising that as you deform the parameters of the foliation, you recover the quantum toric varieties. And in fact, quantum toric varieties were first defined by me using this approach in a much previous paper that only later developed into what I have been telling you. But this was the first way in which we saw the quantum toric varieties. All the ones, and let me just say that essentially they come from an LBM manifold if and only if the fan comes from a polytope. So this is exactly the, unsurprisingly, unsurprisingly, well, from LBM manifold you can recover quantum toric varieties, but which ones can you recover? And this is the theorem. It uses some deep results of Ishida. Quantum torics recovered from these LBM manifolds are exactly the ones that are Kähler as stacks, and there is exactly the ones in which the fan comes from a polytope. And now we are totally ready to introduce the modular space and so on, and study a little bit the topology and the geometry of the modular space. But I guess for today, that's enough. Thank you very much.
Thank you.